Hi friends, good morning, back with another video. It's been a long time I have uploaded the video on HEC RAS and the stormwater design. So in this part of the video I'm going to show you the 2D Culvert model, the new version of the HEC RAS, that is HEC RAS 6.2. Here if you see this RAS mapper window, I'm considering a small section of a creek. So in this small section of a creek, across across this creek, there is a high ground level. You can see here, you can see this magenta color line indicating the high ground level where I'm going to model a 2D culvert. So for this 2D unsteady flow 2D model, I'm considering the boundary condition that at the upstream it will be flow hydrograph, and at the downstream there will be considering the normal depth, that is I'm assuming the energy slope condition at the downstream. So let's begin this tutorial.
Now time to create 2D geometry here. So I am going to draw a 2D polygon across my section of the river, section of the creek. So I'll select this geometry, add new geometry, just name it as 2D flow area. 2D flow area. Okay. Okay, I've created a 2D flow area, and here you select this 2D flow area here, and in the perimeter create the project area polygon, and on this polygon we are going to construct or generate the mesh points. Okay, so for 2D model, just consider the section of the creek. I will draw a polygon. I'll name this perimeter as flow area 2D. Okay, and here for this grid spacing I will take a random number. I am taking a large number because if I take a smaller number the computation takes much time, so that's why I'm considering the large grid spacing. So that means I can reduce my computation time, and result would be approximate. If you reduce this grid cell spacing, there will be more number of grids, and in that case your model would be much more accurate. Okay, I'm just want to construct a typical approximate model. Okay, so just I will consider the grid cell spacing as 45 feet, and I will consider this Manning's roughness coefficient as 0.5 and generate all the grid cell points. Okay, I have generated all the grid cell points. Now I just want to compute the hydraulic property table here. Okay, and also close it, and also turn on the computation mesh points to check if any errors, or if to check if any grid cell is having more than 8 faces. In that case it shows a error in the below tab, or if a mesh point is, if a mesh cell is having more than 2 computation point, then it is an error. So we need to check it briefly here. So there is no such issues. So now just select it, stop editing, and we will save this our edit. Okay, so here we have created a geometry of the 2D polygon, that is our section of the creek, and we have generated the computation mesh points. So computation mesh points will generate the hydraulic property table for this each individual cells. So now I will save this RAS mapper geometry here, this file, and save it. And now I will move to geometry. We already geometry data. Here I will open that geometry data from the RAS mapper. So here you can see I have imported the same RAS mapper geometry into HEC RAS geometry. So before that I will just move to this RAS mapper once, and I forgot to define the boundary conditions at the upstream and downstream. I will do that quickly here. So this is the upstream, and this is the downstream. So flow is route from this upstream to downstream, and here I will define a boundary condition. Just is this boundary condition, it's here. I'll just define a boundary condition, edit left to right along the direction of the flow. So here the upstream, I'll just consider a boundary condition. Okay, upstream, and at the downstream, just turn off this. Yes, at the downstream, flow hydrograph. So I'll just mention it as a downstream. So downstream I am going to consider the normal depth condition. Just save it and stop edit. Yes, so save this geometry. Once again move to here. So here you can see the boundary condition is automatically created in the HEC RAS geometry, because we have updated the boundary condition in RAS mapper. So automatically it is created in HEC RAS geometrical window. So now it's time to add the culvert. So this is the high ground level where I'm going to model a culvert. So to do that, just here, just select this 2D area and select this storage area 2D connection. So just select this, and this is my high ground level. So I'm going to model a culvert here. So I'm just taking a culvert 2D. Okay, and select it, and just enforce all the connection as a 2D break line. Okay, so we have defined this, and here you can see we have defined the, so we have to adjust this And here the main catch is the here we have to adjust the computation point away from the embankment point, that is the deck part of this culvert. So we need to push these mesh points away from the deck part of the culvert. So to do that we need to keep these mesh points away and within the stream zone, not in the high ground level. So we need to shift this. So to do that we will remove some of the points and make it on the away from this high ground level. So to do that, just edit move object or remove points. So you can remove the points here, just remove the points, remove some of the points. Okay, so we have removed the points. And here why I have pushed these computation points which are near to this high ground level away, and shift that mesh point to the channel portion, because in that case in the when we run the model, so in such cases it is a possibility that there will be cell error between the weir and the invert of the culvert barrel. So that's why I have pushed these computation points away from this high ground level. So here you can see on either side I have pushed this the nearest computation point which is on the high ground level, and shifted it to the stream portion, that is the Talweg line of the stream. So instead of high ground level I shifted it on the Talweg line of the streams. Okay, all right. So now I'm select this, and I will select this and move to this storage area to the connection. Here you can see, here we are getting the profile of it. So this is showing the profile of the weir. So here I will create a weir embankment out of it. Here before that I need to select this cut profile from the terrain. Okay, so it will create the embankment here, and here I will consider the top width. So to top width, so what is the top width of the weir? So I'll just move to here. I'll select this one, measure tool. So it's a 52.3. So I'll just approximately take it as a 53 feet is the top width, or I will mention it as say 55 approximate, 1 degree higher. Okay, 55. So we have defined the weir here. So next we need to define the culvert barrel. So here I am considering the culvert as a circular pipe, and it's a circular pipe with a square edge entrance head wall. Okay, so I will consider the square edge with entrance head wall, and I am considering the diameter as 2 feet, and the culvert length. So culvert length should be more than the weir length. So weir length we have selected it as a 55. So I will consider the culvert length as slightly above this 55.6, or I will consider it as a 56. Entrance current of coefficient I will just consider 0.3. So you can refer this HEC RAS manual to know how to consider the entrance loss coefficient and exit loss. Here is I'm just considering the trial case. And at the top, the Manning's roughness coefficient, it is 0.013. So this is the Manning's at the top, which indicates the wear portion, the Manning's roughness for the wear portion. So when culvert starts overflowing above the deck portion, that is the when the flow passes over the crest portion of the culvert, in that case it consider the roughness coefficient 0.013. When it is passing below the culvert surface, barrel surface, then it is considering 0.013. So here I am by default consider both as a same Manning's roughness. So here is the upstream inward elevation and the downstream inward elevation. I need to define it. So just I will go here. I will I'll just select this. I will press shift and I will check this profile. So here is the profile here. This is my embankment. It is the high-rise ground level where I'm going to model a culvert. I'm just considering the approximate inward level here at the upstream. This is the upstream and this is the downstream. So at the upstream I will consider this. I'll redo that once. Okay, so here I will consider upstream, it is 165, and I will consider at the downstream it is approximately 164.52. Okay, so I'll just consider, okay, 165 feet inward level at the upstream and 164.52 inward level at the downstream. Again I need to fill this 55.7. this barrel left diameter is 2 feet and entrance coefficient of roughly assume 0.3, 0.013. Here I am not considering any special case, so just it will be depth blocked is 0, 0, so I'm not considering any special cases here. So culvert barrel 1, culvert barrel 1. I will consider the station here. So station is upstream. I'll just approximately take this 60 feet. It's the upstream station. Downstream station same as 60 feet. Culvert barrel 2 seems I will consider it as a 65 feet upstream and 65 feet. This is a horizontal station. These are considered based on a horizontal station. So 60 feet is the approximately here one culvert is coming, and this is the top surface of the deck portion of the weir or embankment or a deck portion, and below which the culvert is installing. We are installing the culverts. And culvert barrel 3, culvert barrel 3 I will consider as 70 feet station at the upstream and 70 feet. So this is the horizontal stationing of the location. Then it is nothing but it is a center line station. So from this 60 meter center line station, so it is considering the diameter of culvert barrel opening, it is 2 feet at the inward elevation of 165 to at the downstream and 165 elevation at the upstream. Okay, So here you can see the culvert barrel. So I need to increase. I can provide much larger dia pipe here. I will just provide some larger dia pipe here. Instead of that, I will just consider 3 feet pipe, 3 feet diameter of the pipe. Okay, so this looks somewhat better, and I will also increase this length, culvert barrel length, so culvert length to some higher degree. Culvert length I will increase it to 57. Okay, yes, this is somewhat better. So 57. So we have defined. Okay, so this is the location. So the weirs are set up. It is the deck portion of the culvert is set up. Here consider the wear corona coefficient is 3 feet. We consider wear coefficient as 3. The wear width as 55 feet. Their crest shape as broad crested. Okay, and regarding the culvert size, so we have considered diameter of the culvert as 3 feet in dia, the culvert length as 57 meters, so this length should be more than the wear length. And here we have considered the entrance loss coefficient, so I just want you to confirm it from the reference manual, so please check that one. So it varies based on the conditions. Also this exist loss coefficient, and here I have let it system to compute the flow control. Either I can select these 3 of the option, inlet control or outlet control. So here I am considering the compute the flow control. Okay, and here I have assigned the inward level at the upstream and inward level at the downstream, and this is the horizontal station, that is the location of the center point of the culvert along the with respect to horizontal alignment. So this regarding this with respect to this x-axis, this is the station. So these are the one is there the 60, first barrel is at 60 feet and second is at 65 feet approximately this location, and the third one is 70 feet. Okay, all are set up. Okay, just close it, save this geometry. Okay, now move to this edit data, edit unsteady flow, save this unsteady flow as unsteady. Okay, so okay, fine, can just okay. So at the upstream, so here flow the area. At the downstream I am considering the normal depth, that is the energy slope condition. I just assume the friction slope of the bed is 0.03 here. Okay, and at the upstream I will consider the flow hydrograph as I mentioned earlier, fixed start time as just consider 24 0.08 08. So this is the random flow hydrograph I'm considering here. Okay, I'll just paste it here. And I will also add the energy slope here. I'll just consider the energy slope same as the downstream energy slope. I just did the approximate one. So here you can see the flow hydrograph pattern. So it's just a random one I have selected and added it in this model. Okay, just move to this unsteady flow, edit unsteady flow, save this flow data, close it. Okay, now time to run the model. So what I just want to check the is up to 24 point. Okay, just I will do this small simulation. Okay, unsteady flow, just save this plan. I mentioned it as trial. Okay, trial. Okay, select this on 24 25. I just select a random period between these between the time series data. So I will just select this start as 0.0800, and in between I'll just consider a 22. Okay, 22. Just select a time period and I'll just consider it computation point. So I'll consider 1 second computation points. This also affect the stability of the model and accuracy of the model, this computation interval. So here I will just want the output at 30 minutes and okay, and just I'll go to this computation tolerance option 2D. I will select this as shallow water equation, that is momentum equation. This is a full dynamic equation it solves, and yes, okay, I need to check it. So okay, so here I need to change this time as 24. Okay, so I have selected beyond the limit of the my data, so that's why it was causing error. Now it is fixed. Save plan. Okay, so we'll run the model now. So it takes some time to run the model. So we have run the simulation. There are some minor errors are there. So some minor errors in the storage. So let it be as it is. You can use some, you can arrange the mesh, or you can arrange the computation time interval, or you can even increase or change or alter this theta, that is the stable model stabilizer. So you can change this to within 0.721, so to make it to vanish that storage errors. So I here in this example I'm just want to show you the typical and approximate model, not a exact one. So that's why I'm considering the rough estimation, rough computation parameters. So there is some minor errors are there. So now move to this RAS mapper window and check the results here. Okay, just results. I'll just turn on this plan. This is the maximum one. Just I will turn on this and run the model. Okay, just run the model. So here you can see the simulation. So here I will add the culvert here. Just add the culvert barrels. So here is the culvert barrel. So here is the culvert barrel. It's an approximate model I have built. So here I will just adjust this hydraulic property table. This tab, I will change it and update the elevation. Okay, so it is, the units are in feet. All right, so here you can see it's approximate method I have considered. Okay, here is the boundary condition. At the upstream you have considered the flow hydrograph, and at the downstream you have considered the normal depth condition. So just run the simulation once again. Just you can see the simulation run, and you can do this particle size tracing. Since it is an approximate method, so you can't find much in the, you can't find the vortex flow even though we run in the full dynamic model. So here you can see the simulation run of culvert in HEC RAS 2D. That is the new version of the HEC RAS. So thank you for watching.